Hey guys, Justin here, and welcome to our take on the Hot Ones challenge. I'm joined here by Michael, and we are going to be doing all 10 sauces from the show Hot Ones. If you haven't seen that, here's how it works. There are 10 sauces in increasing intensity that you eat a wing from, but in our case, Michael is vegan, so we're going to be eating vegan chicken nuggets. But because this is a math channel, I'm not just going to ask 10 questions. We're going to do 5 questions in 5 math problems. So let's go ahead and eat our first hot sauce, and then I will ask our first question. So our first hot sauce is called the Classic Chili Maple Edition and is rated at 1,600 Scoville heat units. I feel like it's your traditional hot sauce.
Yeah. They're not trying to do too much with it.
All right, so let's get into our first question. So the first question I have prepared is, why did you start a math YouTube channel?
So I originally started the channel in order to flip my classes. And so for you guys that are not familiar with the process, so lectures are put online, and then students come prepared to immediately start working on problems. And so, that's what we did. So I made some lecture videos, and then I flipped my classes, and students came in and they worked on problems together, and it was great. So not only did students learn the material really well, but I feel like they also became more acquainted with each other and built some sort of community around the class, which was like really my goal. Now, looking back on it, I think nowadays, one of my main reasons for keeping with the channel is like to produce content that like a younger me that would like. So when I was younger, there wasn't so much the internet. The internet wasn't as big as it is now. And I think that had I been around as a kid in the time of the internet, I would have eaten up math and science content and I would have loved it. So I kind of think about that when I'm making content nowadays, for people like me.
Yeah, I think that education is kind of outdated in the sense that we don't teach students, or students aren't really taught to utilize the internet as a resource properly in the classroom. I find that like the public schools that try to do it don't end up doing it properly. And I think that videos like this, where you go into depth and you kind of like doing math that is harder than you're used to, is really beneficial for developing those skill sets as early as you possibly can. So let's go ahead and eat our second sauce, and then Michael will do a math problem for us. So this second sauce is called Sinai Gourmet Tropicante, and it is rated at 4,000 Scoville heat units.
So I think this is meant to be a little bit tropical. It has a pineapple on the front of the bottle. So it does have a tropical flavor. It's nice. Okay, so for our first math problem, we're going to look at the antiderivative of the cosine of the natural log. And we're going to do this using complex function methods. So let's recall that e to the ix is equal to the cosine of x plus I times the sine of x. So that's Euler's formula for the complex exponential. But that tells us that the cosine of x is equal to the so-called real part of e to the ix. That's if x is a real variable, which we're assuming inside of our antiderivative. So what we'll do here is rewrite this as the real part of the antiderivative of e to the I natural log of x. So I've got e to the I natural log of x instead of e to the ix. Perhaps I should have put theta here to see the substitution more seamlessly, but I think it's okay. Okay, but now we can use exponent rules to simplify this. So notice the exponent rules will take this multiplier of I and bring it into the natural log as an exponent. But now the e and the natural log will cancel each other, and we'll have the real part of the antiderivative of x to the I dx. Now we can use the power rule on this. We can use the power rule as long as the exponent is not equal to -1. So let's see, that's going to give us the real part of 1 over I plus 1 times x to the I plus 1. So we have something like that. So now let's bring that down here, and as we bring it down here, let's multiply this constant by 1 minus I in the numerator as well as the denominator. And we're going to do that so that we only have complex numbers in the numerator. That's easier to work with. So that'll give us the real part of, let's see, 1 plus I times 1 minus I is 1/2. Let's go ahead and take that out. And then we'll be left with the real part of 1 minus I times x to the I times x. We can write x to the I plus 1 as x to the I times x, but This x, like we said, is a real variable, so I'll factor that out as well. Okay, but now let's recall that this x to the I was really just e to the natural log of x times I. So we can re-expand that. So just to reiterate, this x to the I is e to the natural log of x to the I. In other words, e to the I natural log of x. So that'll give us x over 2, and then we'll have the real part of 1 minus I times, well, e to the I natural log of x, which we can expand as the cosine of natural log of x, and then plus I times the sine of natural log of x. Great. And now from here, what we'd like to do is extract the real part. So notice we get a real part from the number 1 times cosine, and we get a real part from minus I times I sine. But minus I times I is plus 1, so in the end we'll have x over 2 cos natural log of x plus sine natural log of x. Then we can't forget the plus a constant. And that would be the final value of this antiderivative.
All right, thanks, Michael. So let's go ahead and get into our third sauce now. This sauce is called Microsaucery Pico Peppers Pico Rico and is rated at 15,500 Scoville heat units.
And there's a cat on the label here.
Yeah, hopefully that'll be up on screen for you to see, but it's a really interesting looking bottle.
Okay, that one ratcheted it up a little bit. It's still not so bad. I will admit that I'm not so good at hot foods, but I'm a little surprised how well I'm doing so far. I'm sure it will all come tumbling down a bit later.
I will say my goal for today's video is to not drink a single bit of the milk.
That is not my goal.
For better or for worse, I feel like my role is to be the interviewer who is not affected by hot sauce, so we'll just see how that goes. So my second question for you, Michael, is have you felt imposter syndrome? And if so, how have you dealt with it?
I have felt imposter syndrome, and I think everyone feels imposter syndrome for a different reason. But mine stems from the fact that although I'm not a first-generation college student, my mom went back to college after my parents divorced when she was in her 40s and became an elementary school teacher. She was the first person in my family to go to college. So that being said, I didn't grow up with a big history or a lot of generational knowledge of higher education. So I went to a university that was, had a lot of students that were first generational, and I didn't really feel out of place there. But once I got to grad school and was around students that went to really fancy undergraduate colleges, I definitely felt out of place and felt like I had imposter syndrome. And that stayed with me for a while, even after I got my PhD, when I was at, my first conferences. It did get better after a while, maybe just with time, maybe after I had produced some results that led to publications and felt like I had done something that I deserved to be there, which is a little bit of a bad way to look at it because you always deserve to be there. But that being said, time is what helped me, time in doing things and getting comfortable in those situations and really being okay with being uncomfortable for a couple of years until I met people and had contacts at conferences and felt okay. I would say mostly I don't feel imposter syndrome so much anymore, except when I'm around academics from other fields, like for instance the humanities. I definitely feel imposter syndrome around those guys. They use so big words and they also are so good at speaking off the cuff, and I feel like that's not one of my skills. But that being said, I think I've essentially gotten over it at this point, but it took a long time.
Well, I feel like that's also because you teach at a liberal arts college, not just a regular technical college. So there's a lot more people that are really esteemed academia type people at the liberal arts college because they're drawn to that kind of aesthetic. But I think that's a really good message to put out there, that if you're struggling with imposter syndrome, it does get better, and that you just need to put yourself out there and keep trying and you'll get there, and not to worry about it. Everybody's in different places, and you and the person next to you struggle with different things. So don't worry about comparing yourself to those people around you. But before we get to our next math problem, let's get into our next hot sauce. So this number 4 hot sauce is Los Calientes Barbacoa, and it is rated at 33,000 Scoville heat units. So we're ratcheting it up a little bit here.
So it's got a nice barbecue flavor. I like that one. That one might be my favorite so far.
It's kind of sweet.
Okay, so for our next math problem, we are going to prove that there are infinitely many primes of the form 4n plus 3. So let's write that down. Infinitely many primes that are, I'll just say, congruent to 3 modulo 4. In other words, of the form 4n plus 3. Now, there's a really general result that would allow us to solve this in one step called Dirichlet's theorem, which says that there are infinitely many primes of the form an plus b, but we won't use that. That's when a and b are relatively prime. We're going to do this from scratch. We're going to use the classic proof, which goes by way of contradiction. So by way of contradiction, let's suppose that P1 all the way up to Pn are all such primes. So in other words, we only have finitely many. So that's the assumption that we're making, that there are only finitely many, and that should lead to a contradiction, meaning that there are infinitely many. Now the trick here is to construct a number which will lead us to a contradiction. And the number that works here goes like this. So let's set n equal to 12 times P1 up to Pn minus 1. Now let's notice that this is most definitely congruent to -1 mod 4, but the fact that it's congruent to -1 mod 4 means it's congruent to 3 modulo 4. Great. But now let's recall, or let's think about this. If all of the factors of n were of the form 4n plus 1, then n would also be of the form 4n plus 1, or it would be 1 mod 4. And that's because those types of numbers form a closed set. So that means there must be at least one prime of n, or prime dividing n, that is of the form 4n plus 3, or 3 mod 4. So let's do that. So let's summarize that here. So we must have a prime p that divides n, and p is congruent to 3 mod 4. Again, because otherwise n wouldn't be 3 mod 4. Okay. But then, since this is all such primes, that tells us that p must in fact be equal to pi for some I between 1 and n. But now let's notice that p not only divides n, but p also divides 12 times p1 up to pn, right? So because it's one of those factors there. But if it divides both of those, then it's going to divide, maybe this 12 times the product minus n, which is equal to 1. So that means p divides 1. But that's problematic because we've got a prime dividing 1. Well, in fact, the only positive number that divides 1 is 1. So our prime is equal to 1, but 1's not a prime. 1 isn't prime or composite, it's called a unit. But 1 is also not of the form 3 mod 4. So that is our contradiction. So what did we contradict? Well, this original assumption up here that there were finitely many primes, that means there are actually infinitely many primes.
All right, awesome. So let's get into our next sauce here. So our number 5 sauce is called Fly by Jing, and it is rated at 46,000 Scoville heat units. So not quite as much of a jump as the last one, but still going to be ratcheting it up a little bit.
I like that one. It's a nice sesame flavor. I think the sesame oil makes it not seem as hot at first, but then it's kicking in. Yeah.
Yeah, it's definitely got an interesting flavor.
Is that one my new favorite? I don't know. The barbacoa and that one, those are both pretty good.
So that brings us to our third question. So my third question for you is, what kind of music do you like, and kind of how do you use it in your day-to-day life?
So I would say my musical tastes nowadays are mostly like indie rock. So if I were to point out some bands that I really like right now, there's a band called Typhoon. They're from Portland, Oregon that I really like. I really like Phoebe Bridgers. I really like Belle and Sebastian. They've been around for a long time. I really like Deltron. 3030 I think is the best hip hop album of all time. It's my hot take. My musical tastes probably formed when I was in high school. There was like a vibrant, very, very young DIY punk and hardcore scene in Little Rock, Arkansas, and that sort of had me going to see lots of bands play, probably like every weekend, maybe both days on the weekend sometimes. So I've seen like many bands play in a small park down by a river in Little Rock, Arkansas. Don't listen to that type of music so much anymore, but still that like formed my musical sensibilities.
Yeah, I feel like the music you listen to growing up can kind of shape your personality sometimes, and not necessarily in a bad way, but like I think that it's an expression of yourself, what kind of music you like to listen to. So I think that's really interesting. I personally have never been to a concert, so I can't really relate to the experience of seeing all these cool bands play. Maybe we should go sometime, but I think that's really cool. So let's go ahead and get into our sixth sauce here before you do our next math problem. So our sixth sauce is called Chili Laguna de Fuego, the turmeric bomb, and it's rated at 69,000 Scoville heat units.
Okay, this one is getting hotter. This one did not seem to have as interesting a flavor as the other ones. It's mostly just really hot so far. What do you think, Justin?
I actually think it does have an interesting flavor. It, to me, tastes like a combination of peppers and things, kind of relating it weirdly to like salsa. It has a very interesting, I agree, hot, but it has depth to the flavor is what I'm trying to say.
What are we at, 7? Is this 7 or 8?
The next one will be 7.
Oh, this is 6.
And
cool.
The bomb is 8. That's the big one.
Cool. So we want to find all complex numbers A such that this matrix A, 2A, negative 1A, is diagonalizable. So if this was not a 2 by 2 matrix, this would be quite a bit more difficult, but because this is a 2 by 2 matrix, this is not so bad. What we need is for A to have 2 eigenvalues. So need A to have 2 different eigenvalues. If they're complex conjugates, that's fine. That means it's diagonalizable over the complex numbers. If they're real numbers, that's also fine. That means it's diagonalizable over real numbers. If they have the same eigenvalue, then that means that it diagonalizes to a multiple of the identity matrix, but you can only diagonalize to a multiple of the identity matrix if you are already a multiple of the identity matrix. So that's pretty easy to show. So how do we find out if it has 2 different eigenvalues? We look at the characteristic polynomial. So let's recall that PAX is equal to the determinant of x times the identity matrix minus A. So that's going to be equal to the determinant of, let's see, x minus 2, A minus, or that should be a minus A now, and then a plus 1, and then x minus 1. Okay, so let's take that determinant. That will be equal to x minus 2 times x minus 1 plus A by determinant rules. Now let's multiply this out. This gives us x squared. I believe it's minus 3x plus 2 plus A. So how do we know how many roots this has? So the roots of this will be the eigenvalues. So we'll look at the discriminant of this polynomial. So the discriminant of this polynomial, if it's equal to 0, we only have 1 root, and thus it's not diagonalizable. So let's see, our discriminant will be b squared minus 4ac, so that'll be 9 minus 4 times a plus 2. We want that to be equal to 0. So let's see, that's going to give us 9 minus 8, so that'll be 1 minus 4a equals 0, which tells us that a is equal to 1/4. So it's not diagonalizable. No, not diagonalizable. In this case right here where a is 1/4, it is diagonalizable everywhere else. Okay.
All right, so before we get into our next sauce and our next question, I want to do a progress check. How are you feeling, Michael?
You know, not too bad. Like that last one like hit me hard at the beginning, but you know, it wore off a little bit while I was doing the math problem. I don't know if like talking helps, like it creates saliva or something to like dilute it, but not so bad right now.
Well, that's a good thing because the next sauce that we're doing is the first one that kicks up into the 100,000 Scoville range. So our next sauce, number 7, is called Cosmic Disco, and it is rated at 103,000 Scoville heat units.
Okay.
Interesting.
Is it though?
Yeah, it has kind of, I guess if I were to describe it one word, it would be cool.
It's not the word I would use.
I just like to have the flavor sit in my mouth for a while.
That one also just felt hot to me. Didn't feel like any flavor.
So my fourth question for you today is, why did you decide to go vegan? And when did you go vegan?
Yeah, good question. I like to say that I'm the original vegan. Obviously, that's not true. I went vegan in 1997. So I was part of the punk rock scene in Little Rock, Arkansas, as described in the last question. And I'd say I just like originally became vegan because it was like a thing to do as part of that friend group that I had. That being said, that's not a reason to stay vegan. So I stayed vegan throughout the years because, you know, I think it's the right thing to do. I think environmentally, I think ethically, for like reducing harm, being nicer to the animals and such. You know, I really think it's like that. So I don't know if anyone out there has watched Buffy the Vampire Slayer, but there's a vampire who got a chip put in his head so he couldn't attack the humans. And then over time, from not attacking humans, he just became a good guy. So I feel like that's what it was with me being vegan. Started being vegan just as like kind of a thing to do. But then over time, I recognized that it aligned with what I thought was like the right way to live my life.
Yeah, me personally, I'm not a vegan. We're very different on the foods that we eat, but I don't know. I'm kind of glad to be eating these vegan nuggets instead of trying to eat an actual wing. I feel like it'd be harder to do with the sauce on it for sure.
Yeah, I can't speak to that.
All right, before we get into this next sauce, which is the bomb, which is supposed to be
where it really ratchets it up.
Yeah, which is supposed to be the one that like knocks everybody's socks off. Let's do another progress check. How are you feeling after that 100,000 Scoville?
So now the heat is carrying over. All right. I feel like I'm visibly uncomfortable.
Oh, for sure.
Yeah. And this is not an act. Yeah, it hurts.
Yeah, I mean, I'm carrying a lot of heat on my palate. My nose just started running, which I thought was going to happen way earlier, but my mouth is definitely in a good amount of pain, but it's not anything too bad. I'm not in like physical discomfort yet. I do want to drop my fact for the day here for those of you at home. I did a little research on the chemical that produces like the heat in peppers. And the effect that it can have when you have it in the higher doses that we're about to get here is it can actually kind of constrict the blood flow in your brain and give you kind of like a caffeine, like high kind of adrenaline rush type feeling, which is really interesting. And it can actually produce headaches after the fact. So yeah, so you might have some after effects after this as well.
Looking forward to it.
Okay, so let's get into Da Bomb, as it is titled. So it's called Da Bomb Evolution. It is rated at 135,600 Scoville heat units. I think we're about to feel every single one of those heat units.
Is this maybe the time where I don't eat the whole nugget? Not for Justin. Oh, there's a lot on there. There's a lot. Okay. Okay.
Would you like to describe the taste?
It's just hot. I think is the taste. Although maybe it'll kick it. Yeah, it's kicking in, but it doesn't feel so much worse than the last one, I will admit.
If the last one in a word was cool, this one is fire for sure.
So for our next problem, we're going to show that the intersection of, okay, it's, now that I'm talking more, it's worse, of normal subgroups is a normal subgroup. So we'll just take as a fact that the intersection of subgroups is a subgroup and just prove the normality condition. Let's maybe recall the normality condition first. So we say N is a normal subgroup of G, and we use that notation, the little triangle thing, if for all little g in G, we have the left coset Gn is the same thing as the right coset in G, but that's equivalent to saying that if you conjugate N by G, you get G, so you get N. There are a couple more things that's equivalent to for all little n in N, G inverse little n, G is in N. And that's what we'll use, the last one. That's the most helpful here. Could you pour more in here, dude?
Sure can.
All right. So let's suppose that N and M are normal in G, and that G is in G, and maybe N is in M intersect N. But notice that means that G inverse N, G is in M because M is normal, and G inverse NG is in N because N is normal. But then by the definition of intersection, that means G inverse N, G is in M intersect N, but that's the normality condition. So that means that M intersect N is normal in G, which is what we wanted to show. So what's the takeaway here? These problems seem hard at first when you're just learning a subject, but if you take a step back and just remember all of the basic definitions and play around with each one until you find the one that works really well, it should be okay. And that's exactly what we did here. We used this last definition, and we used the definition of intersection. So this is pro tip, I guess.
All right, Michael, I have to say you're doing well. You're hanging in there. You know, I'm in a lot of pain too, even though I don't feel like I'm showing it as much as you are right now. I can't imagine trying to think through math with this much pepper, but I do have to say this is where it gets hard, because this next sauce, number 9, is called Pucker Butt Pepper Company Unique Garlic, and it is rated at 642,000 Scoville heat units. That makes it like nearly 5 times as hot as the last one if we take this as a linear unit of measure, which I don't think it is.
Is it, though? I don't know. Post in the comments if you know what scale we should be using. Is it linear or logarithmic, or...
How are you feeling now? I think you're starting to get a little more side effects here from the heat. I could see you like maybe starting to tear up a little bit.
Yeah.
Is it time to grab some supplies? Do you want me to grab you something for your eyes or something like that?
No, I'm okay. It's funny, like, my nose is running a little bit, but my eyes are not really tearing that much. It's really condensed into my mouth.
Yeah, for sure. That's where I feel it the most. And I think that's just going to keep getting worse. I hate to be the one to tell you. But so I don't want to wait any longer. I know you've been looking forward to this. Let's go ahead and get into this 9th sauce.
Did you eat the whole thing? That's cool, I guess. Tough guy.
Oh, garlic is the right name for it.
That one started off bad.
I think because of the flavor, it's not as bad as the bomb for me.
There's this lull before it starts to really hurt every time. We've lost all sense of flavor. I hate to say it. That might be just my palate. Not really knowing hot sauces, though.
No, I feel like I got a little bit of garlic there. I think the spicier food is, the harder it is to put flavor in it. Yeah. You know, if the defining thing you're doing with increasingly hot peppers is put in like more, the more capsaicin you put in, it's like the defining flavor, so to speak. So the heat is the taste of the pepper. But yeah, so let me ask my 5th and final question. Then we'll get into our last sauce, and you can get through the last math problem. So the fifth question is, what brought you here? How did you get here?
Yeah, so well, this is my basement. I just walked downstairs.
Well, here in life, here in location, I mean, like, what do you think is like...
Yeah, that's a good question.
What puts wind in your sails?
What puts wind in my sails? I don't know. What got me here? So, you know, I hate to admit that, like, went to grad school after college because I didn't really want a real job yet, and then kind of just stuck with that. I kind of lucked into a nice job in like nice colleges after grad school. And when I say I lucked into them, that's really true. I totally lucked into them. Both of my first jobs out of grad school were, I got like in the summer before they started, which is like way, way, way too late to be comfortable. I think one of them I got in June and one of them I got in July. And like job applications are generally due like in November or something. So I was just like super lucky. So I'd say luck got me here. Why did I choose this path? I don't know. I think I just really like doing math, and I really like teaching people how to do math. I really like seeing people's face light up when they understand something. Really like building communities in my classroom. Really like being in distress while I'm not answering this question very well.
Don't worry about it at all. Well, I do want to point out, I think it's pretty clear that your love for math and for the community comes through. I think that, despite how you might view it yourself, this is not something most people would be able to do or would go through with, this YouTube channel and with the community you've built at the college. I think, I think you've done something special, and that comes from me. I'm a little biased, but I do want to give you that so you don't feel like it's all luck. I think luck guides us along the way a little bit. Makes life a little easier. But I hate to be the one to say it. That's the end of this question, which means it's time to have our 10th and our hottest sauce. Now, for those of you who are not familiar with the show, the last sauce is called The Last Dab. It's called Apollo. It is made from the Apollo pepper, which is made by the same person who made the California Reaper. It's not been officially rated yet, but the estimates are somewhere between 2 and 3 million Scoville in terms of heat for this sauce. So we're at the end. Are you ready? You feel prepared?
I'm as ready as I will ever be.
I'll be honest, my nose is running quite a bit now, but I still feel good. Honestly, I feel like if I'd been drinking milk, I'd be breezing through this.
Yeah, weird challenge you gave yourself. Weird choice there, Justin.
I wonder what it's going to taste like.
It's not going to taste like anything. It's just going to be very hot. It doesn't look like there's any sauce on there.
The name Apollo is pretty good, pretty accurate. Yeah, it's hot. All right, you can do it. You can get through this math problem. I believe in you.
Okay. So I thought for this last math problem, we would do something related to, my field of research was vertex operator algebras. I thought we would show the generating field alpha of z from the Heisenberg vertex algebra is self-local. So this is using quite a few fancy words, but I've got like a playlist on vertex algebras if you're interested. So what self-local means is that if we take the commutator of this field with itself, we're able to multiply by a certain power of z minus w and achieve 0. In this case, the power of z minus w is 2. So z minus w squared times this commutator should give us 0. Let's really recall what these fields are first. So by alpha of z, I mean the sum over all integers of alpha n z to the minus n minus 1, where alpha n is a certain linear transformation. The Fourier mode related to, like I said, the generator of the Heisenberg algebra, which models one free boson. And so we have commutation relations between these component operators as follows. So they form a Lie algebra. So alpha m alpha n is m times delta m plus n 0. So in other words, it's 0 unless m plus n is 0. And in other words, unless n is equal to minus m. Okay, so let's do it. So z minus w squared on the commutator of alpha z with alpha w. So that's going to end up being z minus w squared times the sum over all integers m and n. I'll just write it like this. And then the commutator of the component relation. So alpha m alpha n. And then we'll have z to the minus m minus 1 and w to the minus m minus 1. Okay, so that'll give us z squared minus 2zw plus w squared from multiplying out that binomial. And then let's recall that this alpha m alpha n is delta m plus n 0. So that allows us to only consider the case when n is equal to minus m. This should be an n right here. So that's going to collapse this to a single sum. So we've got the sum over all integers of z to the minus m minus 1 and then w to the m minus 1. Like I said, that collapses to a single sum based off of this delta m plus n 0, this Kronecker delta. Okay, now we're going to multiply this through. That's going to give us the sum as m goes over all integers of z to the minus m plus 1 times w to the m minus 1. So that's from the z squared. And then minus 2, and then we have the sum over all integers of z to the minus m, and then w to the m. Sorry, I should have an m right here. Yeah. So this should be an m delta m plus n 0. Thanks, Justin. So we have an m right here. We have an m right here. Good. Then we'll have plus the sum over all integers of m. And then let's see, it'll be z to the minus m minus 1, w to the m plus 1. Now we're going to reindex, and we'll reindex into this middle sum. So here, that means that for this term, we need to replace m with m plus 1. And then over here, we need to replace m with m minus 1. And we don't have to reindex this part because it's summing over all integers. So let's see. Under this reindex, this is going to turn into the sum of m plus 1 times z to the minus m w to the m. And then this one is going to turn into the sum over m minus 1 of z to the minus m w to the m. But now let's notice that all of these things cancel. So this and this and this cancels, giving us 0. But that's exactly the condition that we wanted.
Alrighty, I guess it's time for me to send us off here. I would like you guys to give Michael a thank you for going through all this and doing all this work for the channel. I think it's hard to see from your guys' side, but a lot of work goes into this, and we do a lot of work, and I think we really wanted to do something special with this challenge, so I hope you enjoyed it. Leave a like, leave a comment if you'd like, and subscribe to the channel if you haven't already. And if you have any ideas for other challenges we could do, please leave them in the comments because we might take you up on it. So I think I can say for all of us that that's a good place to stop.